Welcome. In this video I'm going to show you how you can perform a modified or regular actually Freeman Tukey Goodness-of-Fit Test. The modified version I'll quickly discuss in the appendix. Using Python, and specifically I'm using JupyterLab and Python version 3.11, but this should also work in other ones. This video will mainly focus on how to obtain the output, not so much if you should be using this test. There are quite a lot of different alternatives, and some might even consider this test to have become redundant. So to show you how you can actually still perform the test, I need some example data, so I'll load in pandas, and then an example file, which is the GSS 2012A, because I slightly adjusted it sometimes for examples. And I don't need all the data, I actually only need one nominal field, so I'm going to be using the marital status for that, and I'll show you the value counts. So for example, 314 people opted for divorced. Now I have my own library where I actually have a specific function for this, but I'll go over that in a different video. If you don't want to use my library, but you do want to use libraries, you can use SciPy. And actually SciPy doesn't have a specific function for this, but it has a so-called power divergence test, which has a parameter that you can set to perform the Freeman Tukey set. So let's load in SciPy stats and specifically the power divergence function. I can then actually give it the observed counts and then say that lambda should be Freeman Tukey. It will then give me the statistics, so that's a chi-square value if I'm not mistaken, and the p-value, which is the significance sometimes referred to. If that's below 0.05, which it is, because the e minus 251 indicates I need to multiply this by 1 over 10 to the power of 251, so that's going to be 0 point and then about 250 zeros and then 2919. So very low. Then we would usually reject the null hypothesis, or the assumption about the population, which in this test is that the categories would be equally distributed. Unless you specify expected counts, then it's significantly different than that. Stats models also is another library that you could have used. It has power discrepancy function. Again, not specifically for the Freeman Tukey, but more general one. It does actually require the expected counts, which, because I don't have any specific expectations, I'll simply use the sample size divided by the number of categories. Sample size can easily be attained with sum, and the number of categories with len. I multiply it with len, so I actually get that value the same amount of times as my frequencies are. Then I can feed the function the frequencies and those expected counts, and again specify that I want the Freeman Tukey one. Now, if you don't want to use any libraries, or at least not for calculating this test statistic, then we first of course need to remove that it was a pandas data frame, so I'm going to convert it to a list, and I'm also going to remove any missing values by using this for loop. I need to know the different categories, and you can use a set for that, which will eliminate duplicate values. So these are indeed the 5 categories. Then I need those frequencies, which earlier I did with values counts, but that's actually, I think, from pandas. So let's do a for loop again and simply keep track of the counts using the count function from Python. Then the number of categories is the len and the sum. And now we can also set the expected counts again, similar as before, but in this case I simply do the for loop. Then finally we can calculate the Freeman Tukey statistic. This is the formula. It looks more scary than it actually is. We have everything we need. The Fi are the observed counts, the Ei the expected counts. So we take the square root of each and then subtract the results, square it then, and then add up all of those and then multiply that by 4. So that's exactly being done here. Here's the 4 times that we're summing them all up. The square root is not available in Python directly, but you can raise something to the power of a half and that gives you the same result. So I'm subtracting the two, the observed counts and the expected counts, squaring the result, and that should give us that same chi-square value. The degrees of freedom is simply the number of categories minus 1. And to find then finally the p-value, you could actually do the whole chi-square distribution. I have a separate documentation on that if you really don't want to use it, but most people would use side-by-stats chi-square. It actually then has a survival function which gives you that 2.919. That's the same as before. There are a few different corrections that could also actually be applied. There's E.S. Pearson. He simply suggests to multiply the results with the sample size minus 1 over the sample size. So that's over here being done. And there's a Williams correction, which looks again more scary than it is. The case, the number of categories squared minus 1. So the number of categories squared minus 1 over 6 times the sample size times the degrees of freedom. And the 1 plus. Note with Williams you then actually divide the found chi-square value. Yates is sometimes also referred to, but usually should be restricted to 2 by 2 tables. There are a few small variations. If the observed and expected counts are equal, I would say then leave it the same, and otherwise subtract a half if the observed count is greater, and otherwise add a half. That's being done in this small for loop, and that should give you the corrected version for Yates. And that's, I think, about it. This was all in one big formula. Here are the references. Oh, and that modified version. I came across 2 sources that actually use a slightly different function, as you can see. It looks slightly more scary as well. But it's just adding 1 to the observed counts as well. And instead of doing 4 times at the end, it actually does 4 times the expected counts already inside the summation. So that's a bit different. And then we get actually a slightly lower value. Alright, and that's all there was to it. Hope this was helpful, and thank you for watching.